jump conditional, all sorts of stuff. We're now, we've already learned 17 instructions. All right, so now we're going to cover sort of this one. We're not actually learning any new instructions on this one. This is more just like seeing what a common sort of C programmatic thing, something that you'd use in a C program, how it's going to be represented in an assembly program, right? Because again, if you're wanting to do reverse engineering, what you're going to get is, this sequence of instructions over here. And what you need to do is recognize, okay, that's a for loop, right? All right, so what we have here, I'm just going to go through it quick. Again, like the other ones, we're not going to dig into it super much. So what we have is main, which has no parameters as input, has a single local variable, I. There we go, push ECX, Visual Studio's little allocate space for one D word. All right, and then we do for I equals 0, right? So we know in a for loop, the I equals 0 gets executed exactly once, right? And never again. And then we have while I is less than 10, right? So that less than 10 is checked every time. It's actually checked at the very beginning. Like you can set something like I equals 0 while I is less than 0, and it's going to immediately check that I is, less than 0 or something right before it ever does anything in the beginning. So it's not like gonna, execute print once and then check it. It's going to check it before it ever gets into this loop, into the loop body. So this will be checked at the very beginning and then every subsequent loop. And then the I++ happens at, this, whatever is here happens, every time after you've gone through the loop, basically. So then you execute your printf, and then you execute whatever is, as this third condition of a for loop. So we're going to look through that right here. First two instructions, pretty standard. Push ECX, we know what that does, right? Question or no? No. Okay, so now move 0, an immediate 0, into EVP minus 4. EVP minus 4, local variable, we only have one of those, I. Move 0 into I. Okay, well, we've already seen the for I equals 0, right? Right there. All right, so now immediately we have an unconditional jump. Right? So we're going to jump to 401026. So go down to here. Okay, compare instruction. Okay, this is probably the initial compare of, is I less than 10 or something like that. Okay, compare instruction. Yep, looks like we have XA, which is 10. Compare EVP minus 4, well, that's I, against 10. And then we do a jump if greater than or equal to. So you can kind of line that up in your mind. So over to the whiteboard, Bill. What I did, I hand waved through it before, but for some of these things like compare instructions, like I said, you can think of it like a subtract behind the scenes if you want. Or if you see that there's something coming up like a jump greater than or equal to, you can think of it like, there's an operand between them. So if you're doing compare, A and B, there's some operand here in a box. And you don't know what that operand is going to be until you get down to that conditional jump statement, right? So I do a compare, and then I have, what is this? A jump greater than or equal to, right? So JGE. Jump greater than or equal to. So now I know that into this box, I should be thinking about a greater than or equal to being placed in that box. And so is A greater than or equal to B? Well, our A and B here are, you do EVP minus 4, right? So that's I. So I have I, and then I have XA, which is 10, right? So is I, which is currently set to 0, because the only thing we've done thus far is 0, is 0 greater than or equal to 10? No, it is not. Therefore, this jump greater than or equal to is not going to hold. It's not going to take the jump. So if it's not going to take the jump, what's it going to do? It's going to fall through to the next instruction. So don't take the jump. Fall through the next instruction. And now this is going to say EVP minus 4, that's our I. Move the value, stored in I into ECX. Okay, well that's 0. Put 0 into ECX. Now push 0, and then push something, right? Okay, now backing up a step, why are we pushing two things? Okay, it looks like we're setting up for a printf, right? And we got two parameters to a printf, I, and then a string, right? Some format string. So we pushed ECX, that was a copy of I, and we pushed some pointer, which is probably a pointer to that string, format string. And then we call something, which here it's not telling you all nice that it's printf, but there's only one call in this thing, so it's a call to the printf. And so then, I think I've already asked this question in class before, but, Eric, what is the fact that we have push, push, call, add 8 to ESP? What does that tell you about the calling convention of printf? So we've got a caller, which is passing some variables, or passing some parameters. And then, what does the add ESP8 do at the end?
It clears out the last two variables.
Yep. So that's our cleanup of our stack. And so which calling convention is it when we have the caller pushes the variables and caller cleans them up as well?
That's the caller set. No.
Nope.
Callers.
Nope. CDECL convention. So we had before the CDECL or the standard call conventions, right? We said CDECL is basically caller, that's what you're trying to go for, right? Caller cleans up, standard call is callee cleans up, right? Since we see the caller cleaning it up right here, printf must be a CDECL convention function. All right, so anyways, we called printf, we cleaned up, and then immediately we take an unconditional jump to 40101D. Okay, so 40101D, okay, this is actually jump backwards, right? So we're jumping back to here up where we have this move instruction. So what does the move instruction do? It says take EBP minus 4, that's our I, put it in EAX, then add 1 to EAX, and then put EAX back in EBP minus 4. So what is that? Andrew, what is this sequence of 3 instructions doing here in the C code? Right, so this one, that one, that one. What does that correspond to in our C code?
You're incrementing I.
Yep, so that's the I++, right? We incremented I because we have I++ here, and then the I++ is executed after we do the print, right? So we just did a print, and then we immediately jump up here, we do I++, right? And then now what are we going to do again? We're going to check for whether or not I is now greater than or equal to 10, right? So we're seeing, is it still less than 10? And so then we just drop down again to here. So we did our increment, and now we're again at that compare, which we had jumped to this compare before, right? We had forced a jump from here to there, but now we just do the I++, check the comparison. If we're greater than or equal to, so now what you can guess is, if we're not greater than or equal to, each time we're less than, we're basically going to execute from here, I++, check if it's less than, call the printf, jump back. So this is where the looping comes, right? Every time through here, this is basically our for loop. And then eventually our I will be incremented to the point where I is equal to 10, right? And at that point, this jump greater than or equal to will hold, right? So it'll do I compared to 10, and it'll be equal. Is 10 equal 10? That'll be true. This jump will be taken, and we'll jump to 1040, which is right here. Doing XOR EAX, EAX. That's that special little convention I told you about before, clear out a register. And the reason why it does that, interesting note, defaults to returning 0. So my C code is wrong, right? I declared a return value for main. I say main returns an integer. But I didn't give any return value. I never said return 1, return 0, anything else. The compiler just said, well, this fool didn't put a return value, so I'm going to default him to returning 0. So it clears out the AX register to say, okay, you're returning 0 because you didn't return anything else, but you said you were going to return something. Oh, thanks, compiler. That was nice of you. Returns 0, tears down the locals, tears down the stack frame, returns. Any questions on this example? All right, moving along. So at this point, we know 17 instructions. So that was fast, right? We knew 9 a little while ago. And was it like just after lunch we knew 9, and now we know 17? We're tearing through x86, right? And that's not even counting JCC and all those different forms of JCCs, right? I said I consider you knowing jump greater than, jump 0, jump equal, jump less than. That's all just one instruction to me, right? So you know what we added here was the unconditional jump, which just says we always go to the target, or the conditional jump. Jump less than, jump equal, whatever, where you either go to the target or you, if the condition does not hold, you fall through. And then we learned 2 versions of ways to set flags without actually storing the result anywhere. And so I'm going to quiz people on this, but you know, I didn't ever bother to even know what the behind the scenes were with these until I taught the class. So it's entirely acceptable to not know these. But let's try to go back to our remote people. I'm going to say, let's see, John last time chickened out and disappeared just in time for me to ask him a question. John, for the compare instruction, what is it actually implemented behind the scenes, right? So compare is secretly some other type of instruction, but then it like doesn't store the results. So what is that other sort of instruction which gets executed when we do a compare?
Subtracting the value.
Okay, I can hear you. Can you say that again?
Subtracting the 2 values.
Yes. So the compare behind the scenes is a subtract. It took him just long enough to look that up in order to answer that question. That's why I can't, you know, ask these questions to the people on the phone. Shouldn't quiz, but oh well. All right, and how about the test instruction? Greg? Is Greg still there? Or was Greg one we were having trouble with the mic? I don't know, but we'll try. Greg, how about the test instruction? What is that behind the scenes? What sort of instruction?
An and?
He said an and. He's the one you can't hear.
Okay. Yeah, I can't remember who. We got 2. We only need one person with a G for their name, then I'll remember. Yes, it is an and instruction. The test instruction is just an and, where we don't store the results. We set the flags accordingly. And then we go ahead and, you know, potentially do potentially do like a conditional jump or something like that after that. And then and or XOR not. Those are just typical Boolean logic, so I'm not going to go into this. There we go. 2, 4, 6, 8, 9 equals 8. All right. Now we're going to, now we have 2 surprise instructions here, kind of not, depending on how much you know about the behind the scenes. So now we have some simple C code where we have 3 variables. We take A, set it to 40, then we do A times 8, and then we do that's equal to B, and then B divided by 16 equals C. So we did some multiplies and divides here, but just like the first time we were trying, you know, frantically to get a multiply instruction, we do not have a multiply. What we have are these shift instructions. So there's a shift left and a shift right. And so somehow, some way, the compiler decided that for my multiply and my divide, I would be better suited by having a shift instruction. So let's see why that's the case. So first of all, you can explicitly use shift things, and that's why I said you may know about this already if you've done a bit of C coding. You can use, say, the shift left by doing this less than sign. So it's saying shift that way, shift left, right? So if you use those, well, so the first operand of a shift instruction is the source and the destination. And it's like a register or a, I believe it can be an RM32 as well. Maybe incorrect on that, but we'll see. So the first operand is the source and the destination. The second operand is the number of bits that you want to shift the source by and then take whatever the result is and put it into the destination. And so what it turns out is for each bit that you shift something to the left, that's equivalent to multiplying it by a power of 2. Well, by 2. For 1 bit movement, that's multiplying it by 2. And so if you move, say, 3 bits, that's multiplying it by 2 to the 3. If you move 5 bits, that's 2 to the 5. And so over to the board, let's see why that is. I mean, so if you remember what the underlying description of binary things are, you know, you've got, 1, 0, 1, 0, something like that. Right? And so if we remember, this is actually 0 times 2 to the 0. Right? So 2 to the 0, yes. 1. 2 to the 1, which is 2. And this is, 2 to the 2, which is 4. Right? So it's 0 or 1, 2, well, let's call it 1, 2, 4, 8, 16, 32, right? So each of these is a power of 2 increase, right? 2 to the 3. So this right here, this is, let's see, I think that's A. That looks like 10 to me because it's 10, 10, so I'm pretty sure it's 10. Let's check. 8 plus 2, 10. All right? So we've got 10 right now. We've got 10, and if I shift this over by 1 bit, each of these things by 1 bit, well, whereas previously I had 1, 2 to the 3 and 1, 2 to the 1, right? So I had an 8 and I had a 2. If I move everything over by 1 bit, I go 1, 0, 1, 0, 0, and then whatever else, right? Now I have 1, 2 to the 4, which is 16. And then I have 1, 2 to the 2, which is 4, which is 4, and that plus that equals 20, right? So I've only shifted the things over by 1 bit, but my 10 has become a 20. I've multiplied it by 2, essentially. For every bit that I shifted over, it becomes 2. And you can see why that's the case, in the very naive case, right? If I have the number 1, right? If I move the number 1 over by 1 bit, it becomes 2. If I move the number 1 over by 2 bits, it becomes 4, right? Because now I have, if I move this over to this point, I have 1, 0, 0, right? I now have 1, 2 to the 2. So for every bit you move over, that's the power of 2 that you're multiplying it by. So the compiler knows that it's actually very fast and efficient to just take bits and move them one direction or the other. And so when it sees that you're trying to do a multiplication by a power of 2, which in my original assembly, I was trying to multiply times 8. Well, that's 2 to the 3, so it knows it can just shift it over 3 places, right? And it knows I want to divide by power of 2, 16, which is 2 to the 4. Therefore, it can shift it the other direction 4 places. And that's essentially what it did. You have shift, shift left by 3, and then later on a shift right by 4. So shifting, 1 bit at a time is just multiplying or dividing by a power of 2. However many bits, that's 2 to the number of bits. So again, I just have some simple examples here. If we had hex 33 and we moved everything over by 2 bits, right? So shift 33 over by 2, we get CC because it's, break that down, that's an 8 and a 4, that's C, that's 12, and then an 8 and a 4, that's C, that's 12. So the other thing I need to say about this sort of shifting, so for left shifting is different from right shifting, but whenever you're left shifting, basically whatever the last bit was, like where do the bits go when they get shifted out of the register and stuff like that, right? So if we pretend we have 8-bit registers here rather than 32 bits, right? When you shift things over by 2 places here, you treat those like a, 2 1-bit shifts. And so this top thing, at each shift, that carry flag, which is, again, one of those flags we said we didn't care about before, but now here's a simple case where we can understand it easily. The carry flag will be set to whatever the topmost bit is that you happen to shift off at the time. So, you know, in this case, it's, you know, 0, 0, so carry flag is 0 at the end, nothing particularly complex about it, but, you know, if I had something like, you know, 1, 0, 0, 0, 0, 0, right? If I had that number, which you know what that is, 8, 0, 8, 0, right? If I did this shift by 1, right, that value was, you know, x80, right? And I shifted it by 1, and the carry flag, you know, gets set to 1, but now the result thing equals 0. And so the reason why we do this shifting over into the carry flag is to kind of say, like, look, x80 multiplied by 2 is not 0, right? But we need to have some way to know something happened here, right? This is not, you know, the fact that this flag is set to 1 is trying to kind of tell you, like, look, I have zeros in all these things now, but that doesn't mean, like, the real value is 0. The real value is 1, 0, 0, 0, but I can't represent, you know, 9 bits of data in this 8-bit register. So treat this kind of like, you know, one extra bit that'll tell you if this thing happened to just go a little bit too far. It overflowed the bounds of what is possible to represent in this, right? So x80 times 2 is too big to represent in 8 bits, and therefore you use 9 bits to represent it. So the carry flag is kind of like an extra little bit there so that you don't, like, lose values and stuff, right? You don't want to ever, like, have it be the case that you multiply something and the result is too big and, like, somehow the results just become invalid, right? You need to have somewhere to, like, catch these extra bits so that your computations don't just become invalid all of a sudden. I mean, that said, the programmer themselves can be writing stuff which results in invalid things, right? If the programmer decides to write, you know, I have a single character and I'm storing 80 in it, and now I want to multiply it by 2, well, you know, that can be the programmer's error in that case. Anyways. And so the main thing here, like I said, is just treat, you know, a 3-bit shift, right? So we had here a 3-bit left shift. Treat that like, you know, 3 independent 1-bit shifts, or, you know, just think to yourself, well, whatever was 3 bits over before, that's going to get stuck into the carry flag. So in this case, right, we're shifting by 2, and therefore, so I guess that's what I'm trying to kind of say in these bottom parts right here. I have the exact same 2 instructions here, and one of them I shift stuff, you know, over by 2, and that's fine because I shift this and carry flag gets 0, and then carry flag gets 0, and then that's 1, and everything's fine. In this case, I shifted it, and the value is too big, and therefore carry flag gets set to 1. But still, you know, you didn't, like, lose some data about what the correct value should have been. But it's entirely possible to lose data, right? If you shift too many things, right? If I would have shifted this by 4, well, I caught the carry bit the first time, but the next time I shift it again, now it's like way, way too big, and I can't even represent it in 9 bits of information, right? And therefore, I'm just losing information at that point. So that's shift left. This is shift right. Now, I called this shift logical left, and this I'm going to call shift logical right. There is a difference between logical and what I think we cover it in the next section, and I think that's going to be next tomorrow. But there's a difference between logical shifts and arithmetic shifts, as we'll see later. Logical are kind of the unsigned shifts of the world, and arithmetic, as we'll see later, are the signed shifts. So again, hardware doesn't care. It's bits moving around one way or the other. The compiler needs to either generate, you know, if it's multiplying negative numbers, that value may, you know, -1 times 2 better equal -2. It better not, you know, turn into a positive value and stuff like that. So there's different shifts for positive or negative. C doesn't actually care about that, right? You can still use the same operator on positive or negative, but the compiler cares because the compiler is the one who's in charge of enforcing that signedness. And therefore, the compiler will generate different shifts, whether it's signed values you're shifting or unsigned values. So anyways, like we said, oh, and one thing about this actually is when you're shifting right, opposite direction, right? So I could take this this 20, right, and I could shift it, let's say, right 3 bits. Right? So I could go 1, 2, 3, and I can shift that stuff too far to the right as well. Well, now that the helpful carry flag just magically appeared at this side of the thing this time, and now the carry flag caught that one over here, and you know this is 0. Right? So you can shift too far that way as well, and the carry flag will catch stuff because you divided it too much, stuff like that. So, yep, that's all I want to say about those. So, going through this quickly, nothing amazing here. Standard function prologue, subtract, ESP, subtract, question? Yeah.
Sorry, just a quick question, because I don't think I caught this. I'm sorry if you said it. If I shift something that ends in a 1 right, it knocks that last one into the carry flag.
Yep.
And then I shift left again. Is it smart enough to pull it back?
I believe so. So the question is like, well, let me think now. No, so the arithmetic one is smart enough to do that. The logical one is not. So the logical shifts, when I shift this way, you always get zeros from this side. When I shift that way, you always get zeros from this side. So where the smartness of the arithmetic version comes in is that that's smart enough to take whatever the carry flag was, and like it repeats that. Well, okay, actually that's not even true. Well, you could call it repeating that. See, I'm not even sure now. I'm going to have to test this to be 100% certain on it. I only thought about it in terms of the right shift. Let's see, right shift. I believe left shift is always the same, and you always get zeros on the least significant bits. So it's not going to be taking the carry flag and putting it, you know, a 1 sometimes on the bottom. I think like the rotate instruction, which we don't go over in this thing, I think that does it actually. But yeah, so with logical left shift, you always get zeros coming in from the bottom, right? So however many bits I shift this over, those bits that were undefined before, those get filled in with zeros. And similarly here, you know, when I shift this over, I always get zeros coming in from this side. And I don't even know for sure. Yeah, I'm pretty sure with the arithmetic one, it's not reading the carry flag to decide which it puts in here. The arithmetic flag, spoiler alert, the arithmetic flag, plug your ears if you don't want to hear this. The arithmetic shift says whatever the most significant bit is. So if I had a value like this, and I right shifted this, say 2 bits this way, this would turn into this. This is shift arithmetic right, which we'll see tomorrow. Shift arithmetic right says whatever the most significant bit was at the time you decided to start shifting, I'm just going to replicate that into those bits that come in from that side. Whereas the logical one just says you get zeros. And this one, it'll say whatever that bit was. So if that bit was 0, you get zeros. If that bit was 1, you get 1s. But the logical shift doesn't care. You get zeros. Because it's unsummed. And it'll make sense a little more tomorrow. Accumulating a collection here. All right. Any other questions on shifts? All right. So going back to this quick. Standard function prologue, subtracting 12 from ESP to allocate room for our 3 variables, 4 sized each. Taking, moving hex 40 into EVP minus 4. Hex 40, EVP minus 4, that's A. Moving A into EAX, right? So A into EAX, shifting it by 3. So A shifting by 3 is multiplying by 8, right? 2 to the 3. We're going to take A times 8, which is equal to A shifted left by 3. And then we, you know, place that back. Well, so we place that into B, right? So now we have A times 8 into B. So take that EAX after the shift, right? Because this still replaced EAX with whatever that multiplied by 8 version was. And then we put that into B, which is EVP minus 8. And then now again, you know, just naive, simple, unoptimized stuff. We put it into B, and then we read it back out of B. And then we shift the opposite way, and then we store that into C, and then we're pretty much done, right? So we shifted ECX, which was B, shift it right by 4, that's 2 to the 4 division. Take ECX, put it into C, and then we're returning C in this one. So read from C, put it into EAX, which is our return register, and then go ahead, tear down the locals, right? And here we can finally kind of see the efficiency of this construction of the move EBP to ESP, right? I said before that destroys your locals irrespective of how big they are, right? So finally we have, you know, more than one or maybe two things, right? So it just says take ESP and set it to EABP, and therefore everything below that, which would have been your local variables, gets all wiped out, right? We're back here pointing at, the stack pointer points at frame pointer. They're all pointing at the same thing. Therefore, all your locals got destroyed in one instruction. And then pop from EBP, take your saved version, put it back in EBP, and then return. All right, any questions again? See, we got 7, and then we have 8. Yeah. Okay, so we may get through 8 today. Probably won't get through 9. All right, so we said if you're going to multiply or divide by a power of 2, the compiler is smart enough to do shifting, right? So let's try to get a multiply or divide instruction by not multiplying or dividing by a power of 2. So pretty much the same thing, except we moved it down to one variable again. So a times 6, not a power of 2, so we're going to get a multiply instruction. A divided by 3, not a power of 2, we're going to get a divide instruction. So let's go over these. We have imul, which is assigned multiply. And you're supposed to say, wait, what? And you go back and you say unsigned int a. So unsigned variable times 6. You're giving me assigned multiply? That don't make no sense. Well, I don't know. I don't know what I've been told. The Visual Studio doesn't like unsigned multiply. I don't know. I couldn't get it to generate any unsigned multiplies in just simple code. I'm sure if I had like some mega complex code, I could probably get it eventually. But this just seems to be a predilection of Visual Studio again, just like its little pushing ECX for single local variable. So it doesn't like unsigned multiply, even though I have, you know, unsigned operators and stuff like that. I took two variables, both unsigned, multiplied them by each other. Didn't get an unsigned multiply. So whatever. So we've got a signed multiply, and there's 3 forms of this. And this signed multiply is sort of an oddball, actually, because this is the only form of something that can take 3 operands, actually. So usually you see 2 operands where, you know, you take operand 1, operand 2, and you put the, you know, whatever the operator is in between the 2, and you store it back into operand 1, right? So this is the kind of weird one. So the simple case is imul, give it an RM32. And in this case, it implicitly is going to say, I'm going to take EAX, and I'm going to multiply it by whatever RM32 you give me. And remember, RM32 could be just a plain register, so it could be EBX, or it could be the value at memory pointed to by EBX, right? And it's going to take that, it's going to multiply EAX times whatever you give it, and stick it into EDX EAX. And it's because they have EDX in front of EAX here that I was unsure earlier on which way, like if you're returning a 64-bit value, which side is supposed to go first. But anyways, you basically just concatenate these things, because the point is, you can see with multiplies, when you're multiplying two 32-bit numbers, you can have the result be not representable in 32 bits pretty quickly, right? So, you know, there's plenty of cases where you're going to overflow the bounds of 32 bits, so that's why they store it in a 64-bit value. So that's the first form, where your 64-bit value is the EDX concatenated with EAX. And, you know, they're each put in, it's basically just half of the result is put in one, half of the result is other, and you are supposed to interpret it as being concatenated, or more accurately, the compiler will interpret the thing if you try to use a 64-bit number or something like that. All right, second form is basically the same thing, except instead of the implicit EAX, which exists in the first form, right? First form, you just give it something you want to multiply EAX by. This time, you can give it the register that you want to multiply by this other RM32 form. So here I could say like EBX times, you know, the memory at EBX or something like that. And the result will be put back into the register. Now again, like I just said with this past one, you know, you could overflow this register pretty easily, right? So if the compiler is going to be doing it that way, it needs, you know, the compiler needs to be smart about it's choosing this form where you're putting the result into the 32-bit thing because it knows that the result can be something represented by 32 bits. So it needs to be smart about that, basically. And then the third form, which is what makes IMUL be the oddball, is that you can take an RM32 and an immediate and put it into some other register, right? So there's this 3-value form, whereas previously we said that always, this first operand is going to be the destination as well. Here, you've got an RM32, you multiply it by an immediate, say 2 or 5 or 27 or whatever you want, and then you put the result into the register that you specify. So that turns out to be the version which we got this time, for whatever reason. So it took so what is this saying? It's saying EAX times 6 and then putting it into EAX. So why didn't they just choose, why didn't they choose the first form, Amy? Why do you think?
Well, they probably didn't choose the first one because it's multiplying it by 6 but I don't know why it didn't.
Okay. Well, so yeah, one reason you could say, well, this kind of goes to both of them, right? So one reason you could say is it probably, well, let's see. It knew that, multiplying, well, no, I wouldn't say that necessarily. I mean, yes, it could have been smart enough, right? But you can have some number represented in 32 bits that when multiplied by 6 is greater than 30 bits, right? FFFFFF, right? Multiply that by 6, pretend that's an unsigned number. Multiply it by 6. Well, but the thing is, this only deals in signed numbers, right? So maybe actually that is the case. But it's 2 billion times 6, yeah, that's greater than 4 billion. So no, you can still overflow at 5.
Yeah, but you did just set it to a constant.
Right. So, and then kind of related to that, why it may not have picked the second one is, so kind of related to both of these is that you've got the 6, and that 6 is an immediate, right? And that 6 was used as an immediate in the C code, right? So you hard-coded a 6 into your thing, and the compiler is probably just going to be dumb and say, well, you have a 6 in your code, and I'm going to use a 6 as an immediate in mine. And there's only one way to use an immediate in this, right? So what it could have done is it could have, moved 6 into, memory or something like that, and then it could have used the RM32 form to get it back out and multiply it by something, right? And so it could have done that, but, really, why compilers do anything is we cannot fathom the whys or the wherefores. There's a nerd somewhere who he thought to himself, this is how I'm going to translate this C sequence, right? Anyways, then there's just a few examples of these. Yes, question?
So, if the actual likely reason for it choosing the third form here is there was an immediate in the C code,
Yep.
and the immediate in the C code was something much, much larger than 6, is there any way to make sure that the compiler doesn't put you in a case where you might have an overflow on the back end? Or are we just trusting the compiler smart enough to...
Right, so you said put it in the case where the compiler doesn't generate an overflow on the back end. The thing is, generating an overflow is just fine if that's the way you coded it, right? You can take 2 values and you can say, please multiply these values for me, and they will always overflow, right? And the compiler will indicate that with like an overflow flag, which we didn't talk about in the E flags, right? So the compiler is just, trying to be as literal in terms of what you told it to do, and you can tell it to do something where you force it to overflow, and it's not going to, stop you from doing that, because that's what you asked it to do, basically. Yep. All right. Anyways, just a couple of, one version of each of these, basically. So we say, if we had just IMUL, if you just saw the instruction IMUL ECX, this, you would have to assume, has to be the first form, because the first form takes only one operand, right? And there's only one way to take one operand for this, right? If there's one operand, it must be the first form, and if it is the first form, the calculation it must be doing is EAX times whatever this is. It could be, brackets, it could not be. Here it's not bracketed. So it's an RM32 just specifying a register, ECX. So EAX times ECX, put the result into EDX, EAX, concatenated. And so here I'm saying that, here I guess I did explicitly try to overflow it, overflow 32 bits at least. So I said the value hex 4400000 when multiplied by the value in ECX, which is just 4, I'm just assuming it here, right? I'm assuming both of these values. If you do 44000 times 4, the result is 1. Well, it's greater than anything you can put in 32 bits, so it's 1 in EDX, and then it's 1000 in EAX, right? So you've multiplied and you have a result that's too big to represent in EAX. That's why the thing puts it into EDX, EAX. And so then we just have a couple other forms as well. I guess it looks like we're not going to get to the next example today, so that's fine. All right, so the other forms are, so if I see the 2 version form, right, again, there's only one version for each of these. There's a 1 version, 1 operand, 2 operands, 3 operands. And so you know that the translation for each of those is if it's 1 operand, you're doing this. If it's 2 operands, you're doing this. If it's 3 operands, you're doing that, right? So therefore, this 2 operand version must be taking EAX times ECX and putting it into EAX, right? And yes, that could potentially overflow, and if it potentially would, then you would maybe need to do some manipulations to not overflow that, to change it into the first form, for instance. And I'm kind of curious on that, and I probably have to go back to that and try to play with that a bit and see if I can force it to use one form or the other based on, like it'll use this if it's too small, but if I don't use an immediate, if I go back and I change this code to not use an immediate, I would guess it would use the second form, for instance. If I just like create an A and a B and I multiply A times B, like I set A equal to 1 and I set B equal to 2, I multiply them, I would expect it to use the second form, for instance. We'll see. And then I'm going to change the A and the B so that A times B will obviously overflow, and then I'll see if it still uses the second form. Or you can do that on your own. All right. And then the third form is what we got with ours, except we got EAX. And, but you can have these values be different, right? So our version got EAX, and 6. You can have them be different, right? They don't have to be the same. That's just what happened with ours. So here I'm assuming EAX to be 20, x20. Assuming ECX to be hex 4. Take ECX, which is hex 4, times 6, which is hex 18, right? So 4 times 6 is 24, which is 116, and 1 8 equals 24. So 4 times 6 is hex 18, and it's putting that into EAX, right? ECX stays the same as what it was before. Right? And then the div instruction was generated for the other thing, and that's the unsigned divide. And so there's 2 forms of this. There's one of them which is doing a divide of AX by an RM8 that you specify. So this goes back to those small forms that we're talking about. So you can take AX, a 16-bit value, and divide it by an 8-bit value. And then, you're guaranteed that, the quotient will fit in AL, a 1-byte value, and the remainder will fit in AH, a 1-byte value. And then the bigger form is you take EDX and EAX. I feel like there should be another form, but I need to go check that as well. No, it's because of this quotient thing. Yeah, no. All right. So the other form is you take the 64-bit thing, EDX, EAX, and typically if you're just dividing a 32-bit thing, like the compiler will automatically set EDX to 0, right? You can have a 64-bit value that's 32 bits, and you just set the most significant bits to 0. So you take EDX, EAX, and you divide it by an RM32. So it's a 32-bit value, right? It can either be the value in a register, a value out at memory where the register points. Use the complex form. I guess I didn't put that there, right? But I can do the EBX plus ECX times 4 plus 3042, right? I can calculate something, and it's going to say take the 64-bit thing, and then whatever I've calculated, whether it was a memory address or the value at memory, etc., divide them, and EAX here gets the quotient, right? So the number of times you evenly divided this number by that number, and the EDX gets the remainder, right? However many is left over. So down here, and actually, I hope I fixed this last time. I think there was a problem in this last time. Yeah, I think I fixed it. Maybe not. I think so. Okay, so we're doing the first form. 8 divided by 3. Yeah, that's definitely right. All right, so how many times can you divide 8 by 3? 2 times. No, that's right. So 2 times remainder of 2. Yes. So, back and forth, 1, 3. All right, so last time I had a remainder of 1 or something like that. So, all right, fix the slide. It's not fixed in your slides, so don't trust everything on your slides. So yeah, just take 8 divided by 2, goes in 2 times the remainder of 2. All right, more complex form, div EAX by ECX. Now, it may be written this way, right? You may do div EAX by ECX. It may be written that way, but behind the scenes, it's EDX EAX, right? So if your compiler didn't like set EDX to 0 immediately before this, you can get the wrong value, right? So the compiler is responsible for, if it's knowing that it's doing a 32-bit divide, it better set that EDX to 0, because otherwise it'll be messed up. Yes?
If you put something other than EAX as the first argument, will you get EDX concatenated with whatever else you passed in?
No. Yeah, so the question is, can you say EBX here, div EBX, something like that? No. So this is actually not something where you're actually allowed to change that. It's just writing it this way to like tell you, look, I'm going to be using EAX as the thing that I'm going to be dividing by, basically. So yep, you don't have configurability of that parameter here. Like I said, these are the only 2 forms of the, and therefore it's going to be dividing EDX concatenated with EAX by the RM32. All right, so that was pretty much it for what we're going to do for today. We're going to get into this example 2 tomorrow. We're going to learn about, we're going to see how much more complicated this, if we don't turn off those compiler options and stuff that I was saying, we must turn off, sanity checks and things like that. This very simple program right here, turns into that program. This is the extra compiler-generated sanity checking stuff that gets added in. So we're going to figure out what's the deal with that. So it gets turned into that. In reality, this is what it should have been, right? If we had turned off the sanity check additions that it added in, this would be the thing. It would just standard stack frame, allocate some space, set something to something else, return hex blood. Okay? That's all that does, right? Allocate some stack space for your buffer, set buffer 39 to 42, return blood. Very simple code, but if you don't turn it off, if you have the sanity checks turned on, you get this. We're going to dig into what's the deal with that tomorrow. All right, any questions before we go today? Actually, before we go, I also have homework for you. So, any other questions before I assign homework for tonight? No, I am not capable of not assigning homework for tonight. Any questions from anyone on the phone? All right, so your homework for tonight is, let's see if I have it towards the end. Simple program is complex or simple as you want. Copy programs from the internet, whatever. I don't care how you do it. Make a program which, when you disassemble it, gives you new instructions that we haven't covered in class, with the following caveats. All right? So what I'm claiming here is that we've really covered pretty much all of the instructions you're going to see if you just write some simple C code. Okay. The following caveats. You may not generate SAL or SAR. These are the shift arithmetic left or right. And realistically, you're not going to create a shift arithmetic left because it's the same thing as the shift logical left, so whatever. Can't create shift arithmetic right because we're doing that tomorrow. Yeah, and this is probably not printed in your things for those who have printed copies. Floating points are off limits, right? So you can't just define a float and then say, oh, look, I have a floating point multiply when I multiplied my float by something, right? Because, like I said, you're typically not going to see floating point things in normal type of code that you'd be reversing and things like that. You typically only see that in like math libraries, things that deal with, floating point numbers. And most programs don't need floating point numbers. We already covered div, right? And so idiv doesn't count. That's like too simple. Change something signed to unsigned, whatever. But null
There's a
would be
question, sorry.
appreciated. Yes, question.
Can we use?
No, you may not, Jeff. You may not use inline assembly. That's cheating as well. And actually, good thing you brought that up because someone actually tried to use. There's like a not inline assembly version of like a macroed RDTSC instruction, which is read timestamp counter. Someone knew like, oh, Windows has a function that I can call called RDTSC, and it turns into the RDTSC instruction. Right? So you may not use inline assembly or things like that. You may not use functions which correspond exactly to one assembly instruction. But that's the only real caveats that I'm going to put on it, basically. So I know what was found most commonly in the previous classes, and we'll see whether you guys generate the same things. You can use Linux or Mac or whatever you want to use. I mean, if you use Mac, you better be using 10.5s because otherwise you're going to be generating 64-bit instructions. But if you're comfortable with Linux and things like that, just go to GCC, make a program, and then go look at my slides and like objdump. Later on, we have the Linux section of my slides. Use objdump-d and dump out your Linux program. That'll just disassemble the program. Or just write it in Visual Studio and do what we've done already. Compile it, show the disassembly, that sort of thing. So, I think it should be reasonably easy to find a couple new instructions. They're going to be some of those minority type instructions, but we'll see how you guys come up with it. So that's the homework for tonight. If there are no more questions, then you are dismissed. All right, have a good night.